Hello, and I'm about to start our talk about Chapter 9, Momentum. Through this chapter, we'll be talking about impulse. We'll define what momentum is. We'll talk about the impulse-momentum theorem. That's supposed to be theorem, not the theory. And we'll discuss the law of conservation of momentum, the first of very important conservation laws in physics. I'll probably get through the first three topics during these video lectures. And the law of conservation of momentum we will do together in class. So to begin with, we're going to define a new quantity called impulse. Impulse is defined because what we've been talking about so far is that forces are either applied to an object or they're not applied. But in reality, if we're, for example, kicking a soccer ball, there is a duration of the kick. The kick lasts for some finite amount of time. It's not an instantaneous thing. We can see that as the foot begins contact, that's the beginning of the force between the foot and the ball. And in fact, the ball even compresses a little bit until the force between the foot and the ball reaches a maximum. We can look at this graph here on the bottom right. And as the ball starts to move away from the foot, contact between the foot and the ball eventually ends. Now, the duration of this contact might only be milliseconds in total, but we call this an impulsive force. And we can define the impulse of this force as the area under this graph. So instead of using I, because I was already taken for moment of inertia, we use the symbol J to define impulse, which is the area under a force versus time curve. Okay? We can sort of approximate the impulse. If we're given a graph of the force versus time, we can approximate this by saying, well, the average force is about halfway between 0 and the maximum. And so the area under here is about the same as the total area here. For those in the calculus supplement, we'll be using integration in order to calculate the impulse more precisely. But for our purposes in this class, we're going to approximate the average force from our impulse graph. From our force graph. So let's see how that works with an example. Let's say we have a half a kilogram hockey puck sliding to the right at 10 meters per second. It is hit with a hockey stick that exerts the force shown here in this graph. What is the average force on the ball? And B, what is the impulse on the ball? Well, to find the average force, we can simply look at our graph and we say, well, it's kind of like a triangle, but I can basically lop off the top, right? So if I draw a little dashed line here and remove this piece, and think about if I made this a square here, all right, this shape looks like it has about the same area as the original graph. So the average force, so the answer to part A, the average force is, I would say, about half of 50 newtons. It's about half of the maximum, so about 25 newtons. Okay, so what is the impulse on the ball? Well, the impulse is simply J. The impulse is equal to the average force times the time duration, the same time duration times the average force. Here's our average force. Okay, here's our delta T. So our delta T is 30 minus 10, that's 20. Let's check the units, milliseconds. So our impulse is 25 newtons times 20 milliseconds. A milli is 10 to the minus 3 seconds. And that's equal to 20 times 25 is 50 is 500. 500 times 10 to the minus 3 is 0.5 Newton seconds. Let's talk a moment about the units of impulse. A Newton second is an appropriate unit. We can also simplify this. Remember, a Newton is a kilogram. This is a Newton second is equal to a kilogram with acceleration. So mass with acceleration is kilogram times meters per second squared. That's a Newton. Multiply that by seconds. This cancels, and we see that the units of impulse are also can be written kilograms times meters per second. Okay, so let's see. That was all I wanted to talk about for this section. See you in a moment.